Alright, welcome. In this video we're going to be working AP Precalculus Homework 1-3. And this is where we're going to be doing all this same analysis of rates of change and stuff. We're just going to have a calculator with us. And we're also going to look at some bottles filling up with water problems. Okay, so first one is the graph of f of x equals x to the 3 minus 3x to the 2 plus 3. There's telling us there's going to be a point of inflection at x equals 1. We're going to need a calculator. And so I get out a graphing calculator, and I'm going to go to y equals, and I'm going to type in the equation. Oh, whoops, clicking on the wrong thing here. Alright, so I'm going to click right here on y equals, type in the equation. Okay, and now I'm going to go to graph. And just look at the picture of this graph and see if I can answer any of these questions without going any further. Okay, so no, I think I'm going to need to, if we're trying to figure out where f is greater than 0, where f is less than 0, this is where the graph is above the x-axis and below the x-axis, right? Because f represents the y-coordinate. So I'm going to go over here and I'm going to need to find the zeros. Okay, so I'm going to go to that and calculate the 0. Okay. I'm going to need to find this one over here. I'm going to need to find all three of them, I guess. So, but I'm going to start over here with this one that looks like it's near -1. If it asks for left bound, I'm going to say -2 because I know -2 is to the left of that 0. Right bound, I'll type in x equals 0 because I know it's in there. And then let it think, and there we've got one. Okay, I'm going to do that again to find the next 0, which will be between 1 and 2. All right, and get 1.347. And then the last one, I would calculate the 0, and that's going to be between 2 and 3. And I get 2.532. But it didn't ask for the zeros, it asked where f is greater than 0 when f is less than 0. So I'm going to I mainly just wrote those numbers down so I wouldn't have to, go looking for them. And so f is going to be, okay, first it asks for greater than 0. Okay, greater than 0 is anywhere over here where the graph is above the x-axis. So that'd be between the first and second zeros. So f is greater than 0 when x is between -0.879 and 1.347. And then also when x is greater than the last 0. Okay, so that was at 2.532. So x greater than 2.532. Okay, and then as far as when f is less than 0, that would be through here. And then this little bit of graph under here as well. All right, so when x is less than -0.879, and also when x is between 1.347 and 2.532. All right, now the next one's going to ask us, where's the rate of change of f positive and where is the rate of change negative? Okay, and this is where I'm going to start by translating because they're giving it to me in terms of rate. I want to talk about what is f doing, what am I looking for on the graph of f, because that's the picture I'm looking at here. Okay, so if the rate of change of f is positive, that means f is increasing. Okay, where the rate of change is negative, that's going to be where the function is decreasing. So I'm just going to translate those right now. And now since we translated it, it's back to, the type of question I may have asked you in Algebra 2. Here's a graph, where's it increasing and decreasing? So what we're going to need to do here is we're going to need to find the coordinates of the maximum and the minimum. Okay, we need this coordinate and that one. It sure looks like 0 and 2, but without knowing how to do calculus, we can't be certain about that. So that's what we have the calculator here for. We're going to calculate a maximum. First one, certainly between -1 and 1. I did between -1 and 0. Don't love that. Yeah, that's not going to be good enough because what if it was just a little bit bigger than 0? Pardon me, we're calculating a maximum between -1 and 1. There we go. And, okay, yeah, so we did get this, and this does not mean 2.27668 times e to the -6. It means times 10 to the -6. Very poor notation. But, times 10 to the -6, that's a very small number. The calculator, it means 0. Okay, so the maximum is happening at x equals 0 and y equals 3. Okay, so if we were interested in where f was increasing, f would be increasing before x equals 0. And then it would be increasing again after it hit that minimum. So I'm going to calculate the x-coordinate of the minimum. That would be choice 3. And it is between 1 and 3. And okay, here we go again with this round off error. Okay, I don't know if you're seeing this on your calculator, but I'm seeing it on mine. This means 2, right? Sometimes the calculator has trouble with like whole numbers and 0 and stuff. Sometimes there's a little round off error. So when x is greater than 2, f resumes increasing. And then f is decreasing only, down here, when it's got this negative slope, it's going downhill as we move left to right between x equals 0 and x equals 2. Yeah, that's still on screen for you. All right, when is f both positive and decreasing? Okay, well, it's decreasing from 0 to 2, but it stopped being positive here at that 0, and I had happened to write that down up above. Yeah, that was 1.347. So I'm going to say, I might even draw a picture of this. It's going to be positive and decreasing kind of through there. Okay, so I'm thinking about starting at the coordinate of the local maximum, which was x equals 0. Oops. And then ending at that 0 of f, which was 1.347. All right, rate of change of f is positive and increasing. Here's where we're getting into just kind of continuing to work on those topics from last time. So rate of change positive, that means f is increasing. And if the rate of change is increasing, that's going to mean f is concave up. All right, so if I'm looking for increasing and concave up, that's going uphill and smiling. Okay, so it's going to look like that. And, oh no, I don't know why I'm thinking, find the graph there, it's over here. And, all right, going uphill is here, but it's frowning the whole time. Okay, so the point of inflection happened at x equals 1. Okay, so it started smiling here, but it was going downhill. So we have to wait for the minimum, which was at x equals 2, and then after that we'll be increasing, like the picture shows. So it'll just be x is greater than 2. Okay. When is f decreasing at a decreasing rate? Okay, so f is decreasing, we don't need to translate that. But the rate is decreasing, that's going to mean to me that f is concave down. So f is decreasing and f is concave down. That's going to look like that. Okay, so that does happen. That would be through here. So it would be after the maximum, because before the maximum, the function is increasing. After the maximum and until the point of inflection. So that would be 0 to 1. What's the average rate of change of f on the interval -1 to 4? Well, we're just going to have the calculator do this job for us. So we're going to quit out to the main menu. We're going to call for a fraction. And we're going to say, all right, compute f of 4 minus f of 1 divided by, f of -1 divided by 4 minus -1. And we can ask it to compute f by calling for y1. So we're going to say y1 of 4 minus y1 of -1 divided by 4 minus -1. And if you're confident that that's 5, you could just divide by 5. All right, I'm just going to try to, keep it in terms of the formula that we're used to, and that's going to be 4. Okay, so now I'm not going to just write 4 here, because in general we need to be showing the setup that leads to our computations when we're computing something on the calculator. So I'm going to say f of 4 minus f of -1 divided by 4 minus -1. That's going to equal evidently positive 4. Okay, leaves the calculator. Find the horizontal distance between the relative maximum and the relative minimum. Okay, that one is somewhat easy on this one because it turned out that it's not a very good sketch, but this happened at x equals 0 and x equals 2. So we can just subtract the x coordinates and find the horizontal distance. So that's going to be 2 minus 0, which is equal to 2. Okay. And now we're going to find the solutions to the equation f of x equals 1. So what we're going to do is we've already got a picture of the graph of f if we went over and hit that button. Let's get a picture of the graph of y equals 1, and then we'll just see where they intersect. Okay, so that's happening 1, 2, 3 times. Okay, so I'm going to have 3 solutions. And so we're going to calculate an intersection, it's choice 5, between blue and red. I'm going to give it a guess of -1, so it starts looking over there and gives me that first one. And there I've got myself a solution. So x equals -0.732. Okay, we can find the next one, calculating the intersection between blue and red with guessing x equals +1. And oh, it was x equals 1. Okay, it's interesting. But I'm sure if we went in and looked at the formula, we would see that when I plug in 1, I'm going to get 1 back. And then we will calculate the third intersection, which will be between blue and red. I'm going to give that a guess of 3. It starts looking over there. Oh, no. Okay, we're going to calculate an intersection between blue and red, giving a guess of 3. And then we get 2.732. All right, and those are my 3 solutions to the equation f of x equals 1. All right, now the next one is saying the intensity of the light coming out of a laser in a science experiment is modeled by n of x equals 10.3 over x squared for x greater than or equal to 1, where n is measured in candelas and x is measured in centimeters. Right, that's not a unit of measurement I was used to. I had to look that up for intensity of light. Okay, so what is the intensity of the light at x equals 3 centimeters? That's a question. We need a question mark. So I'm going to say, all right, well, give me x, so we're looking for n. So it's going to be n of 3 equals, well, I don't know, we're going to use the calculator to find that out. So what I'm going to do, I'm going to plug in the function, I call for a fraction bar, but you don't have to if you don't want. 10.3, you could just use that division, divided by x squared. And then I'm going to quit out to the main menu, and if we just want to have n of 3, now we could go to the table, it would probably be on there, but I just want to remind you that we can just call for y1, plug in 3, and have it compute for us. And then, as always, we're going to round to 3 decimal places. Now that was 1.144. Okay. And then at what distance from the light is the intensity equal to 5 candelas? And all right, so n is the intensity. So we're setting n of x equal to 5, and we're going to solve. Okay. Now we could solve this one directly, but we've got the calculator available to us, so I'm going to suggest we do that. Okay. If you want to solve this one by hand, be my guest. Let's see. Make sure this works on the standard window. Okay, I think it will, yeah. Okay, so this in blue is the graph of n of x. And, well, x is greater than or equal to 1. So I should have been, a little smarter about that. And I should have set the window to be, okay, we just kind of restrict the x values and say 1 to 10. And I think that'll be a lot better for us. So we're not looking at any, values that we're not interested in. And I think the reason for the x greater than or equal to 1 is that there's just certain limitations on this model, and it's not like the intensity of the light is infinite right at the source. So that's just, and that's an idea that we'll talk more about later on as we start to model more situations with functions. All right, so we're going to look for the intersection here to see where n was equal to 5. Okay, so the first curve is blue, which is n of x. The second curve is y equals 5. There's only one intersection, so it doesn't really matter what guess we give it. 1.435. X equals 1.435 centimeters. All right, now find the average rate of change of n on the intervals 1 to 3, 3 to 5, and 5 to 7 indicate units of measure. All right, so this is another thing where I'm going to use the calculator and be smart here. So I'm going to call for a fraction, and y1 of, I'll do 1 to 3 first, minus y1 of 1. And then I think we can do 3 minus 1 in our head, but I'll actually write out what I'm doing here. Over 3 minus 1 is going to equal the first rate of change, and I'm going to divide by 2. Because I can see the width of all of these subintervals is 2, so I'm going to have negative 4.578. Okay. Then the next one would be n of 5 minus n of 3, divided by 5 minus 3. Okay, so that width is also 2. What I'm going to do is I'm going to go back up to here. I'm going to grab that and press enter so it calls for it again. I'm going to go up there and I'm just going to edit 3 to 1 into, that's a lot of clicking for me, but I don't think it would be quite as much for you. 5 to 3, the width is still 2, so I'm not going to change the denominator, and I'm going to get negative 0.366. Then I'm going to do the same thing for 5 to 7. There's going to be hardly enough room to squeeze that in, but I think I can make it work. Okay, so all right, 7 minus y1 of 5 divided by 7 minus 5, and I'm going to get negative 0.101. All right, so is n decreasing at an increasing or decreasing rate? I think that we just all agree that it's self-evident that n is decreasing. Or you look at the definition of n is 10.3 divided by x squared. The bigger x gets, the smaller 10.3 over x squared gets, because the numerator is staying fixed and the denominator is growing larger. And that's another idea we're going to be talking about at length in this course. So as for whether n is decreasing at an increasing or decreasing rate, we can look at the rate of change of the average rates of change on consecutive equal length intervals. That's 1 to 3, 3 to 5, and 5 to 7. So since the rate of change went from negative 4 to negative 0.3 to negative 0.1, we're going from negative closer to 0. So I'm going to say the rate of change of n is increasing. And as a result, we can say n is decreasing at an increasing rate. Oh, and I like this next question. I was kind of proud of myself for this one. So based on its rates of change, could n be a quadratic function? It's got an x squared in it. Okay, so what we're going to need to do is we're going to need to look at the rates of change on consecutive equal length intervals. Look at the second order difference. Okay, if it was going to be quadratic, we would see a constant difference between, the 4.578 to the negative 0.366 and the negative 0.101. Okay, but that's not what we're seeing, right? To go from negative 4.5 to negative 0.366, we had to add 4 point something. Okay, I don't know, 4 point, maybe 2 something, I don't know. Over 4 we had to add. But then over here, when we added here, because the rate was increasing, it looks like I added, 0.265, right, I think. Which is not a constant second order difference, so no. N is not quadratic. Based on the rates of change. The rates of change don't form a linear pattern. Okay, if they did form a linear pattern, those numbers in blue, they'd be equal. Number 3. Object starts at the origin and moves along the x-axis for time t greater than or equal to 0. Here it is again. Okay, so I'm going to need to clear out my calculator. Maybe I should just clear the RAM. Second plus 7, 1, 2. All right. And we've got x of t given by I'll call for a fraction, 50t. Okay, well, we're just going to use x. Know that if our results in x are t values and any of our results in y are actually x of t values. So I know it's still a little confusing for some of us, and that's okay. This is a situation we will become more comfortable with over time, and hopefully next year in Calculus AB it'll be no big deal, or Calculus BC if that's what you decide to take. So find the average rate of change of x on the time interval 0 to 2, and interpret its meaning in the context of the object's motion. All right, well, what we're just going to do an average rate of change over here. Call for a fraction bar. Okay, evaluate, no, not second, it's in F4, so we need the green button. y1 of 2 minus y1 of 0. Now, if you can just figure out what y1 of 0 is going to be, good for you. You can just type that in. Save yourself a little bit of clicking. But then I'm going to divide by 2 minus 0, and then I get 5. Okay, so I'm going to say on this one, x of 2 minus x of 0 divided by 2 minus 0. That's going to equal 5. That's what the calculator is telling me. Now, interpret its meaning in the context of the object's motion. All right, so we didn't really get any units for x, but we could, you could suppose they were inches or feet or whatever you wanted them to be, or meters, or you could just say units. So if it was feet, it'd be, feet per second. Oh no, it was feet from the origin. Okay, so we're gonna let the units guide us. Didn't catch that. Feet per second. And feet per second, that's like a speed, right, or velocity. And so on average, the x-coordinate of the object's position, where it's moving on the x-axis, is increasing 5 feet for each second. 5 y's per x, right? Okay, well, in this case, our y's are x's and our inputs are t's. So, let me write that in. Alternatively, we could have said if the x-coordinate is increasing and we're moving along the x-axis, we're here, and we're moving that way, okay, x is increasing, we're moving to the right. And we could say we're moving to the right at a rate of 5 feet per second on average. Okay, so during the time interval 4 to 5, was the object moving to the right or to the left? Okay, well, I think we could say on average, we could figure that out using the average rate of change from 4 to 5, or we could just look at the net change in position, like x of 5 minus x of 4. And so maybe I'll do both of these things. And so I will say calculate y1 of 5 minus y1 of 4. And get, okay, but what matters, I don't like negative 350 over 341. Okay, now if I don't like that and I want it to become a decimal, I'll just do that. Okay, but what really matters is that it's less than 0. Okay, so negative 1.026. So I would say it moved total to the left. But if we wanted to know on the time interval 4 to 5 if the object was moving to the right or to the left, well, we would need to be looking at a picture of the graph to see if x was increasing or decreasing with respect to time. Okay, what's going on here? Oh, interesting graph. Okay, so what I'm going to do is I'm going to go over here and just press trace and have it take me to t equals 4, right? The input value we usually think of as x, that's the t value, and plug it in 4. All right, and I get 100 over 11, okay? I wish this thing was giving me more decimals, but that's all right. Then I'm going to trace to 5, and I'll go to the right, and I say, okay, I've gone downhill. Okay, so that means that I was decreasing, and you can kind of see on the graph, I mean, we could also just set the window from 4 to 5 if you wanted. And, okay, this was probably a bad idea, but you can see it's going downhill. It's decreasing the whole time. Moving left. because the function x is decreasing. Okay. And then find the time at which the object was farthest to the right. Okay, so if it goes to the right and then it comes back around and starts moving to the left or something, that would be the time when it turned around would be when it was farthest to the right. Or we could say the farthest right place that it goes on the x-axis. Maybe I'll go back to that diagram I've got. Maybe it's right there. That's the farthest right point it achieved. Well, that would be the maximum value of x right there. So what we want is the maximum value of x of t. Remember, x is the output value of this function, so it's going to looking for the maximum on the graph. And so did it say time t greater than or equal to 0? So I'm going to go from 0 to 10. But I also noticed that I couldn't really see the maximum. So I'm going to say, okay, actually cut that off because the other part was in the negative area. Okay, there we go. That's what we needed to see. Okay, but I didn't change the maximum. Okay, so I'm going to press quit. No, wait, you press like you're turning the calculator off, and that stops it from graphing, especially if it's graphing something that's slow. All right, so I need to reset the window again and go from 0 to, I don't know, like 15. Make sure I'm able to see it. Oh, okay, 15 wasn't even enough. Okay, so I'm going to, again, act like I'm turning the calculator off. And I'm going to go into the window and go 0 to 20. I should have gone 0 to 20 in the first place. Should have just doubled it if the first one didn't work. Okay, what's going on here? I am not changing the y coordinate, am I? I'm changing the x coordinate. I'm just being a real fool. Yeah, okay, that was... Okay. It didn't look like it was going that far off the screen. Pardon me, that's embarrassing, but not worth re-recording, right? Okay, so I'm going to go 0 to 15 and y, and then I will definitely be able to see that maximum. Okay, finally. All right. I'm going to calculate a maximum. That's choice 4. The left bound, well, 0 is to the left of it, I know. Let's see. 4 is definitely to the right of it. Giving it a guess. All right, 2.449. All right, so it happens at the point 2.449 and 10.206. Okay, that's the maximum of x of t. And remember that for this, t is the input value and x is the output value. And it asked find the time at which the object was farthest to the right. So the answer to that question is going to be a t value, and it's going to be 2.449. All right. After the object turned around and returned towards the origin, so that's like what it's doing right there at that maximum, it was going to the right because x was increasing, but now x is decreasing, so that means the object's moving to the left. How long did it take after this point that we just wrote down the t coordinate of? How long did it take for the object to move back to x equals 6 feet? Okay, and one thing I'm going to do, I haven't done this yet, I'm going to store the value. I don't think we should need to do this all that much, but I'm going to just type in x and press enter, and notice that that's that 2.449 number. I'm a little worried because this is like very close to 5, and I wouldn't want to be wrong in my last decimal place on the answer for part D, so I don't really want to collect all of the values. What I'm going to do is I'm just going to press X and leave it in this part of the calculator so that I can go back to it a little bit later. Okay, now I need to find out when x is equal to 6. Remember, x is the output value, so I'm going to graph 6 in order to find, okay, this point, because it said after reaching the maximum. So I need to calculate an intersection between blue and red. And one thing I haven't done, okay, that would be one, no, wait, there we go. Is you can just press on the right button and just kind of trace your way over towards a good guess for the intersection, and there we've got it. All right, so in this case, t equals 7.537. But what I'm going to do is I'm going to quit out. If I press X again, okay, it's going to give me the new value of t, okay, because I did a new intersection, okay, or new operation or whatever. what I'm going to do is I'm going to take this value and I'm going to subtract that value. And I'm going to get 5.0878. So in this situation, a valid answer would be, okay, well, so I'm going to actually write in my result. X of t equals 6 at t equals, what was it, 7.537. So the time difference, t2 minus t1 or whatever, that's what I just found over here. That's 5.088. Or 0.87. You're good to just copy the first three decimals you see. Or you can round. On the time interval 10 to 20, is the graph of x of t concave down or concave up? All right, now let's look. We're going to need to change the window because we were only looking from t equals 10 to t equals 20. All right, so we're going to, I don't think 0 to 15 is going to be necessary. I think 0 to 10 should be plenty. And yeah, there we go. Okay, so it's decreasing for sure, but it didn't ask us about whether it was increasing or decreasing. It asked if it was concave up or concave down. Okay, and there's still graphing y equals 6. Well, if I was to put eyes on top of this thing, it wouldn't be smiling all that much, but it would be smiling. It's not frowning, right? The slope is getting less steep, right? So the slope is increasing, and we say the rate of change is increasing. That means concave up. We're just making that decision based on looking at the graph. All right, based on the concavity of x of t, is the rate of change of x increasing or decreasing? Interpret this result in the context of the object's motion. Cool. I hoped I was building up to something there, but I couldn't quite remember. All right, oh, whoops, I zoomed in too much. So, okay, based on the concavity, rate of change is increasing. Physicists would say that the acceleration is positive, but you don't really need to be there yet. That's definitely calculus. What I could say is that x is decreasing at an increasing rate. I could say it's got a negative velocity and a positive acceleration. It's slowing down. Okay, that's really what I'm gonna say. Because its rate of change is negative but increasing. The rate of change is getting closer to 0. Okay, the rate of change of position is velocity, and that's where we're saying, all right, well, objects, it's slowing down. I'm going to just leave it at that, but don't worry about that. That's not something that's just an extension question. Really, that whole page is kind of an extension. This is a different context for us to do a calculator problem. All right, each bottle is filled with liquid at a constant rate. Sketch a graph of depth versus time. All right, now the key with these is to, as we're thinking about the liquid, flowing in through the top, we're going to think about the width of the bottle and how that's changing. Okay, at first, the width of this ink bottle it's pretty wide relative to the rest of the, bottle. At the beginning, it's widest. But what's important is through that height that I've labeled in blue, the width is constant. So the rate at which the bottle is filling will be constant, and the graph will be a line. Okay, then the width decreases, and the width is pretty much the rate at which the bottle is going to be filling up if we're the water is coming in at a constant amount. Okay, so the rate is decreasing. Okay, if the width is decreasing, the rate of wait, no, it's the opposite, isn't it? Yeah, I'm realizing that line was a little too long and a little too steep. I was going to run out of room for my graph. All right, so it's going to be, as the bottle gets narrower, the height will rise faster. Okay, so that means that the rate of depth with respect to time, the rate's increasing, and the graph would be concave up. All right, and then the last part is constant width again, but this width is narrower, so it will go faster than that first line segment. So I'll just go with something with That's supposed to be a line segment. Okay, so straight, curved, straight is the idea here. With conical flask, at the beginning, we've just got kind of the same idea, and I'll try to keep the colors meaning pretty much the same thing. So it starts off and it's very wide, so the height is not going to be going up very fast, but the width is decreasing, so the rate of height going up is increasing, so the graph is going to be concave up. Right? And then at the end, we've got this little bit of, neck here. And so that'll be a constant rate because the width is constant through there. And so it'll probably keep going, at about the same rate and so it's kind of hard for me to, I've got an idea. We'll see if this works. I'm going to have it kind of snap to a line. Okay, yeah, sure. Close enough. All right, for the boiling flask, okay, this one's interesting because this one's, it's got kind of a circular shape and the rest of these are straight lines. What's really important about the shape is not whether it's straight or curved, it's whether the width is getting wider or narrower, whether the width is increasing or decreasing. And for reasons, I guess science reasons or reasons I'm kind of leaving to intuition, the height is going to rise faster when the bottle is narrower. So what I'm saying is we're getting wider here, which is a situation we have not dealt with. So we'll label that in teal. So from the beginning on the way out, okay, the bottle's getting wider. So the rate at which the height is increasing, well, that'll decrease. Increasing at a decreasing rate, okay, increasing and concave down. Okay, so something about like that. But that's probably the wrong idea, right? It's not, the depth is not rising at the middle. So something about like that. Increasing while concave down, but still increasing at the right edge. Then it starts to get narrower, and I've been using red for that, so I'm going to go over here and do this. Okay, so that's when the bottle is getting narrower, the height will be filling up faster. Okay. Depth will be increasing faster, the graph will be concave up. And then at the top, we've got this narrow but short top, I guess. It looks a little shorter than the conical flask. And I guess on the conical flask, it's really time-wise, it's not drawn to scale. It's the length of the black segment's a little too long. I might say it's supposed to be a line segment about like that. That wasn't very good, but that will do. That's the idea. It's supposed to be straight. All right, now the bucket, it's just getting wider the whole time. So I'm going to go grab the teal, label it as getting wider here and there. And all right, so I'm going to turn off the shapes. All right, if it's getting wider, then the graph is going to be concave down. And I don't just love that, but that will do. Okay, that's going to be good enough for us. All right, now let's do the opposite. All right, now before we even do this, I'm going to just jump in front of it saying there's probably a variety of bottles that could have more or less these graphs. I'm just going to be drawing one of them and hopefully a relatively simple bottle. So here, what we need to notice is that this one's concave up the whole time. As a result, okay, the rate at which height is increasing is increasing. Okay, it's increasing at an increasing rate. It's increasing in concave up. So I'm going to say the bottle is getting narrower. That will be a theme. Concave up, narrower, concave down, getting wider. All right, so basically the thing gets narrower. So there's going to be the bottom of my barrel, or not my barrel, my bottle. And it's going to be getting narrower the whole time. So this could be it's a beaker in chemistry class, right? Without a straight top. I don't know. Okay, that's my drawing. It doesn't have to be great. Okay, this one's going to be concave down the whole time. Okay, that means the bottle gets wider as it goes up. Okay, so something like, I think, the bucket and the other one. I do think that this was like originally a matching set, so it's not surprising to me that we would see some of the same ones. Okay, that looks pretty good. All right, this one first is concave up, then concave down. Okay, so concave up is narrower, then concave down. So that means it gets wider. So it gets narrower and then wider. So basically, it's like I stack these two things on top of each other. Say it gets narrower and then it gets wider. So it would look like an hourglass. Maybe. Okay. D is constant rate. Okay, it's linear, and then it's another piece of line. All right, so linear is a constant rate, but then steeper, and so it's still constant again. Okay, so that means if it got faster, right, it's almost like concave up, that means it should get narrower. Okay, so it's gonna go up, and it's gonna have straight sides, is what I'm saying. And then suddenly it's gonna be narrower at that sharp corner there. So I guess it would look like, I don't know how to draw this. Like that, I guess. Okay, that's my best guess at it. Okay, just leave it there. All right, this one's got a bunch of different stuff going on. It goes concave up to concave down, back to concave up. Yeah, so, okay, that's gonna go concave down, which means things getting wider, to concave up, which means I'm getting narrower. Then back to concave down, which means it's getting wider. All right, so I'm gonna draw one side of this thing. All right, this is gonna be the bottom. All right, it's getting wider. That might have been too much bottom, but it'll be all right. Wider, then narrower, and then wider again. Oh, this is, I don't know. Like I've seen pottery look like this before. And getting wider, and then narrower, and then wider again. Okay, that's, and then I could put this thing there. That height would correspond to that first point of inflection on the graph. This ribbon there would correspond to the second point of inflection. All right, that's all I've got. I actually think those are pretty decent sketches for my own art ability. All right, and that's it. Yeah, that's all for this homework set. So that's gonna be all for this video. Thanks for watching. Hope it helped.